Combinatorics onwards seminar. Our speakers today, we have two speakers, Kristina Ago and Bojan Bašić. They are going to speak to us on some results on palindromicity measures.
Thank you. Just let me share the presentation. Is everything okay?
Yes, looks good.
Okay, thank you very much. So we would first like to thank the organizers for kindly inviting us to give a talk at this seminar. And our talk will be about some recent results on some measures of palindromicity of various words. And for the introduction, as we all know, Combinatorics on words is a branch of mathematics that has a very wide scope of applications. And concerning palindromes, for quite a while, palindromes were thought to be just a part of recreational mathematics or something like that. But around the turn of the century, it turned out that palindromes have a major role in the study of Sturmian words, and Sturmian words have various applications in number theory, routing optimization, computer graphics and image processing, pattern recognition, and so on. And there are actually some other examples of applications of palindromes not related to Sturmian words, but here I selected some references with applications of palindromes in various quite disconnected areas, such as quantum physics or molecular biology, or even music theory, and so on. And because of all this, actually a more detailed knowledge about the behavior of palindromes is of a growing importance in recent times. And among various questions arising, one of the questions that we are interested in is given two words. How can we say that one of them is richer in palindromes than the other one, or more packed with palindromes, or something like that? And of course, this question does not have some unique answer. It depends on interpretation of what would mean to be more packed with palindromes. And there are indeed various such measures defined and studied in the literature. And we shall today present some recent results on two such measures. The first one is called palindromic defect, and it is inspired by a result of Drube, Justin, and Pirillo from 2001. They proved that for any finite word, the number of its palindromic factors is bounded above by its length increased by 1. And motivated by this inequality, Brlek and co-authors in 2004 defined palindromic defect, or also called only defect, as the difference between those two values. So the palindromic defect of the word W is the difference of this upper bound for the number of palindromic factors and the exact number of palindromic factors of W. It turns out that these measures behaves very nicely with respect to factorizing the words. In particular, palindromic defect of any word W is greater than or equal to the defect of any of its factors. And this inequality actually provides a natural way to define defect for infinite words. So for any infinite word W, its defect is simply supremum of the defects of all its finite factors. And now let us say something about words of finite defect. If the defect is 0, such words are called full or rich. Actually, full was chronologically the first term, but rich is more common today. And there are many results about such words in the literature. However, infinite words of finite but positive defect have been studied significantly less. So there are not so many results about them. And the reason for that might be the fact that it turns out that explicit constructions of such words are quite deficient in the literature, especially if we add some additional constraint. For example, if we require the word to be aperiodic, since periodic words are, at least in this context, not so interesting for analysis. So with such additional constraints, there are really very few examples in the literature, and in particular, if we consider aperiodic words of finite positive defect, and with one additional constraint that the set of factors is closed under reversal, such combination of properties of words had been deemed quite interesting because of some reasons, but it turned out that examples of words with this combination of properties was quite hard to find. And we shall now show one word that can be called curious for some reasons. Namely, for a period of time, it was thought that if U is any infinite word whose set of factors is closed under reversal and which contains infinitely many palindromes, then it was believed that it is equivalent that the defect of U is finite, and this a little bit technical condition that there exists a constant h such that the longest palindromic suffix of any factor of U whose length is greater than h occurs in that factor V exactly once. But as we shall now see, these two conditions are not equivalent. Let us see why. Let us take a morphism phi defined by phi of 1 is 1, 2, 1, 3, phi of 2 is the empty word, and phi of 3 is 2, 3. So this is we are working on a 3-letter alphabet here, and let U be the fixed point of that morphism that starts with 1. In other words, we first have 1, then we have this, then we have this, then this, then this, and so on. And the word U defined this way has the following properties. First, its set of factors is closed under reversal and contains infinitely many palindromes. Its defect is finite, and this word does not satisfy the condition B. Why? Well, consider this factor here, 2, 3, 1, 2. Its longest palindromic suffix is only the letter 2, and it appears twice in this word. Then consider this factor. Its palindromic suffix is again the letter 2, and it appears 3 times here. Consider this factor. It again has the longest palindromic suffix, only the letter 2, and it appears here 4 times, and so on. We here can find as long factors as we want, whose longest palindromic suffix is only the letter 2, and which appears multiple times in that factors. We shall now say something about uniformly recurrent words of finite defect. Well, there are some results and examples about them in the literature, and there is also quite an interesting result by Pelantova and Starosta from 2012 that says that any uniformly recurrent word of finite defect must be a morphic image of some word of zero defect. And we can say that this theorem actually says that uniformly recurrent words of uniformly recurrent words are in a way pretty tame, and the real fun is actually with words that are not uniformly recurrent, they live in some unexplored territory, and this unexplored territory perhaps deserves a better look. And actually, one example of such word that is not uniformly recurrent is precisely the word from the previous slide. And as far as we know, that word was for quite some time the only known example. And we shall now present a construction from 2013. It's a construction of family of something called highly potential words. So we take any finite word W that is not a palindrome, and we take any letter C that does not appear in W. And we now define recursively W0 is W, and Wi is Wi minus 1 concatenated with C to the power I, concatenated with Wi minus 1 reversed. And then we take HPW of W to be the limit of this sequence of words. The limit here is well defined because it is easy to see that each Wi is indeed a prefix of Wi plus 1. And therefore, we can indeed make this definition. And this is called highly potential word generated by W. Here is an example. If we take W to be AB, then we shall have AB, then C, then BA, then CC, then ABCBA, then CCC, and so on. And what is the point of this class of words? Well, they have some interesting properties. First, each highly potential word has the set of factors closed under reversal. Each highly potential word is recurrent, but none of them is uniformly recurrent. Then each highly potential word is aperiodic, which is now clear. And finally, the defect of each highly potential word is easily calculated. It is just the defect of its generating a word plus 1. In particular, this means that the defect is always finite but positive. Therefore, these words indeed live in that less explored territory, and they seem to be a good supply of examples and counterexamples for various problems on words, which is how they got their name. And to mention just one example, it turns out that each highly potential word presents a counterexample for the equivalence mentioned 3 slides ago. Let us see why. So this is one example of a highly potential word. And we have this factor here, CCABC. Its longest palindromic suffix is only the letter C, and it appears 3 times here. Then we have this factor, whose longest palindromic suffix is again the letter C, which appears 4 times. Then we have this factor, where C appears 5 times, and so on. This holds, again, not only for this word, but for each highly potential word, we can find something like this. Okay, so that's about all the results, and we now move to new ones. We first present the construction of something called generalized highly potential words. They are generated by 4 parameters. So we have 3 finite words, W, U, and V, where not all of them are empty words, and U and V have to be palindromes. And we also have one strictly increasing sequence of positive integers, say A. And we now define W0 is W, and Wi is Wi minus 1, concatenated with this, and then concatenated with Wi minus 1 reversed. And then the limit of this sequence of W's is denoted by GHPW of WUVA, and it is called generalized highly potential word generated by WUV and A. In the following slides, I will often instead of saying generalized highly potential word, we should say simply GHPW sometimes. Here is an example. If W is A, B, U is 1, B is 2, 2, and this sequence A is the sequence of all even positive integers, then GHPW is AB 1, 2, 2, 1, 2, 2, 1, then BA, then 1, 2, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2, 1, then this, and then so on. Okay, so first we shall look at some special cases of this class of words. What is expected is that this class of words contains indeed highly potential words as special case that of course justifies their name. And indeed, if we take this set of parameters, then this GHPW is precisely the highly potential word generated by W. But not only that, it also contains the word from a few slides ago, which we call the curious infinite word. So with this set of parameters, we get precisely that word. And this curious word, actually, I did not mention that, actually is not highly potential word. It has much in common with the class of highly potential words, but it does not belong to that class. And this is not all. In 2009, Glenn and co-authors presented examples of a few words that are rich, recurrent, but not uniformly recurrent. And their examples were first the well-known Cantor word, or also called Sierpinski word, which is defined as a fixed point of dysmorphism. And two more examples also defined as fixed points of submorphisms. So this and this. And the second example was actually taken from an article by Bucci and the co-authors from 2009. And it turns out that all these three examples are actually special cases of generalized highly potential words, namely the Cantor word can be presented like this. And this second example can be presented like this. And this third example can be presented like this. And we hope that all this suggests that this construction of generalized highly potential words indeed extends the class of highly potential words in a fairly noteworthy way. And let us say something about their basic properties. First, we may note that given a particular generalized highly potential word, it could be the case that there are multiple sets of parameters that lead to the same word. So these GHPWs are not uniquely representable by their defining parameters. And if we have some quadruple WUVA, for which W is a palindrome and UV is primitive, in that case, we shall say that GHPW is presented in standard form. So this will be a particularly nice way of presenting GHPWs because it will be very helpful in some results that we shall see soon. What is very good here is that each generalized highly potential word can be presented in standard form. So for each GHPW, we can choose some particular W, U, V, and A in such a way that they generate the considered GHPW and that W is a palindrome and UV is primitive. And we now have the following theorem. It says that each GHPW has the set of factors closed under reversal. It is always recurrent. It can be periodic. And we here have a complete characterization of when GHPW is periodic. Namely, if we assume that it is given in standard form, then it is periodic if and only if W is either this expression or exactly one of W and V is non-empty. And if GHPW is not periodic, then it is aperiodic and actually not uniformly recurrent. So each GHPW is either periodic or not uniformly recurrent, which is good because this means that apart from those that are periodic, all the other ones live on that uninhabited island that we mentioned. And finally, of course, we shall say something about the defect of GHPWs. We here have some technical lemma, let us call it that way. So if GHPW is not periodic and if it is given in standard form, and if we further assume that VU is not a prefix of WUV, so this is a technical assumption, in that case, the lemma says that there exists a positive integer I, such that this factor UV to AIU appears in WI exactly once. Then the factor WI appears in WI plus 1 exactly twice. These first two conditions are quite natural, and the third one is slightly less natural, but we need it. So it says this. And now when we know that such a positive integer I exists, we can formulate the following theorem. So if a non-periodic GHPW is given in standard form, then assuming that VU is not the prefix of WV, so that this technical condition holds, we can then choose the smallest integer I that satisfies 1, 2, and 3 from the previous lemma. And then the defect of GHPW can be calculated in this way. It is actually equal to the defect of WI plus 1. And if VU is a prefix of WUV, so if this condition fails, then it turns out that we can choose W prime, U prime, V prime, and A prime in a particular manner, quite technical for this slide, but actually quite straightforward, not hard. And then for that new set of parameters, we shall have that that V prime, U prime is not a prefix of W prime, U prime, V prime. And the defect of GHPW of W, U, V, and A is the same as the defect of the word generated by this new set of parameters. And this right-hand side defect is then calculated as in the part 1 here. So this is a formula to calculate the defect of any GHPW if it is not periodic. And if it is periodic, then there is also a formula, quite simple. So if it is, say, P to infinity, then the defect of GHPW is simply maximum among defects of all the conjugates of P. And altogether, this theorem actually gives a characterization of all generalized highly potential words that are with zero defect or with non-zero defect, which is, I guess, nice to have. And finally, somebody could ask whether it is hard to give an explicit construction of GHPW which has positive defect, and it is not hard at all to construct some explicit examples. First, if we take any of the words W, U, and V to have positive defect, then it is clear that GHPW will also have positive defect. But this is not the only way. If W, U, and V are all rich, but such that the defect of WU or the defect of UV is positive, then again the defect of GHPW will be positive. And actually it is trivial to see that in general, if WUV are rich, but such that they cannot be factors of the same rich word, then the defect of GHPW is always non-zero, positive, and it was shown by Rukavicka in 2019 that it is decidable whether given two rich words, whether they are factors of the same rich word or not. And there is also an elegant necessary condition by Bucci and the co-authors from 2010. It says that no two different factors of a rich word can have the same longest palindromic prefix and also the same longest palindromic suffix. We have a side note here. It is actually an open question asked by Vesti in 2014, whether this condition is also sufficient. That is, if some words X and Y are given and they have the property that no two of their factors have the same longest palindromic prefix and at the same time the longest palindromic suffix, does that imply that X and Y have to be factors of some rich word, of the same rich word? But this is, as far as we know, still open. Anyway, if this necessary condition is violated for any factors of sum of WV, then we immediately know that the defect of GHPW is non-zero. For example, if W is ABCBA, if U is whatever, and if V is ACA, and if A is whatever, then since W has the factor ABC and V has the factor AC, and those are different factors that have the same longest palindromic prefix, it is A, and the same longest palindromic suffix, it is C, then whatever U is and whatever A is, this GHPW cannot have zero defect. It always has positive defect. And this is all from me. I now give word to Kristina.
Thank you. I will speak about the so-called n-ary ratio. This is a palindromic measure which was introduced by Holub and Sari, and this was defined only for binary words. How it is go? If W is a binary word on the alphabet 0, 1, it is obvious that then W contains a subpalindrome of this length. We can choose either all the letters 1 or all the letters 0. One of those two palindromes will be at least of this length. So we call the W is minimal palindromic if it does not contain a subpalindrome longer than this. Okay. Then RS is called an MP extension of the word W if the concatenation RWS is a minimal palindromic. RS is called an SMP extension if it is an MP extension and the length of the word RS is the least possible. And finally, here is the definition of the n-ary ratio. The n-ary ratio of a given word W is this quotient where RS is some SMP extension of the word W. So these are the definitions. Let's say now some interesting facts about subpalindromes. Holub and Sari proved that every binary minimal palindromic word is abelian unbordered, which is a stronger form of unborderedness. And also they proved that every binary word is characterized, of course, up to reversal by the set of its subpalindromes. And now about the optimal upper bound on the n-ary ratio in the binary case. Holub and Sari proved the following theorem. The n-ary ratio of any binary word is at most 4. What does it mean? It means that every binary word must have an MP extension whose length is at most 4, whose length together with the length of the word W is at most 4 times W. And here is the extension. We put a certain amount of zeros to the left of the word W and a certain amount of ones to the right side of W. It is easy to see that the length of this word is indeed 4 times W and 4 times the length of W. And also it can be checked that this word is minimal palindromic. They also proved that this upper bound is the best possible in asymptotical sense, which means that for every small value epsilon, we always have some enough large word W whose NP ratio is greater than 4 minus epsilon. Okay, these were the earlier results, and now let's try to generalize these definitions to the n-ary case. Okay, now we have an n-ary word on the alphabet 0, 1, and so on, n-1. It is again obvious that then W contains a subpalindrome of this length, so we can say that W is minimal palindromic if it does not contain a subpalindrome longer than this. And it seems that the rest of the definition can be the same as it was in the binary case. But where is the problem? The problem is that it is absolutely unclear whether an NP extension of the word W always exists, and whether the NP ratio is well defined at all. So this is the question, and it was an open problem for longer than 10 years. And last year, we managed to prove that each n-ary word has an NP extension, which proves the well-definedness of the NP ratio for larger arities. And here is the main idea of the proof. Let W be an n-ary word where n is greater than or equal to 4. We left the ternary case for later. We have 2 reasons for it. One of the reasons is that the construction that we will see doesn't work for ternary words, but this is not the main reason. The main reason will be clear very soon. Okay, this is the construction. Let n be a constant defined in this way. Let R and S be these expressions where L's and R's are defined in this way. Quite simple. Then it can be proved that RS is an NP extension of the word W. The proof is very long and very technical, but it works. Okay, here's simple example. For example, for the word 0, 1, 2, 3, 0, our construction gives the following NP extension. And what is the direct consequence of the previous theorem? Beside the well-definedness, we now have some kind of upper bound on the NP ratio for larger arities. So if W is an n-ary word and n is greater than or equal to 4, and n is the constant which is on the slide, then the NP ratio of the word W is not greater than n times m. Okay, the other result that we have is the following. We prove that the optimal upper bound on the NP ratio is not less than 2 times n. And the proof is based on the so-called economic words, which was introduced by Holub and Sari when they proved that 4 is an optimal upper bound for the NP ratio in the binary case. We slightly modified their definitions to make an appropriate version for our proofs. About economic words. So if W is an economic word, then its SMP extension must contain more ones than W. I will skip here all the technicalities and formalities. I will just give a illustration of the proof. Okay, so on one hand, if W is economic, its S&P extension has more ones than W. On the other hand, there exist large enough economic words which have many ones, a negligible amount of zeros, and no other letters. So if this is our word, its S&P extension must contain this many ones. So now we have this many ones, and it can be proved, and it is also quite logic that if we have an S&P extension of some word, it must contain approximately the same amount for each letter. So it means that the S&P extension for our original word must be something like this. And this is this have length 2n times W, which gives the proof for this theorem. Okay. So what we know now, these two results that we have say that the optimal upper bound on the NP ratio for n greater than or equal to 4 is somewhere between 2n and approximately 2 to the n½ times n, and it remains an open problem to narrow or maybe close this gap. And now about the ternary case. Here is the reason why we left it for later. In the ternary case, we have a much stronger result, which says the following. The NP ratio is well defined in ternary case. It is bounded from above by 6, and this upper bound is the best possible. So now if we prove that it is bounded from above by 6, then this last part will follow from our previous result. And how we proved it? We have two constructions, which are these. What is the idea of these constructions? We wanted to them to be of length 6 times W. For example, for the first one, we put all the zeros to the left or the ones to the right side of W and arranged 2's as asymmetrically as we can around W, and G' is some kind of function whose role is to set this value. How can we arrange 2's around W? So what we have to prove? We will prove that one of these constructions is minimal palindromic. And in other words, what does it mean? It means that at least one of them does not contain a subpalindrome whose length is greater than 2 times W. The proof is done by case analysis. First, about subpalindromes of form 0p0 and 1p1. These are the constructions from the previous slide. We proved that the length of an arbitrary subpalindrome of form 0p0 in each of these words is less than or equal to 2 times W, and the same lemma for the palindromes of the form 1p1. But for the subpalindromes of the form 2p2, the problem was much harder. Here we prove that at least one of these constructions does not contain a subpalindrome from 2p2 longer than 2 times W. And to prove this lemma, we needed many sublemmas, And here I will present only the main ingredients of the proof and the main ideas. So it turned out that if you want to prove this lemma, we need the following. If we make a partition of the word W into TU V, and P and Q are subpalindromes of TU and UV. Just to mention, this P is not the same as this P. Okay, then what we need this inequality. So if we have this inequality, then this lemma is true. Okay. Then we made a simple trick. We transformed all the zeros to ones. Why? Because we could do it because if something is a subpalindrome in the word which has letters 0, 1, and 2, it will be a subpalindrome also in the word which has letters 1 and 2. So, and easier to deal with binary words than with ternary words. So this inequality now transforms to this inequality. So we have to prove this inequality. Okay, let's suppose the contrary, that this inequality does not hold. And these two steps are just some algebraic transformations. Okay, what to remember from all this slide? Remember this, we have our word W, U is something in the middle, and what we have now, we now have that, supposing the contrary, that in U we have, let's say, many ones, okay? And, but we have the following theorem. If U is some word on the alphabet 0, 2, TV are some words of the form 2, 2, 2, 2, 2, and P and Q are subpalindromes, let's say enough large together, then this holds. What does it mean? It means that if P and Q are enough large, which is true from the, we have it previously, then in U we have, let's say, not so many ones. And this will give the main contradiction. So now what we have to do, we only have to prove this theorem and we finished everything. Okay, so let's prove this theorem. The proof of this theorem is quite complicated. And I suggest not to read the formulation of the theorems. I will, for each theorem and lemma, on an example, say what does it mean. So first, we define some mappings on palindromes P and Q, which are defined in a particular way. So how does it work? This is our word W. Okay, this is our word W. This part is U, here is T, and here is V. What we have to do, we have to prove that here in U, we have not so many ones, let's say, in this way. Okay, what is P? P is the underlined palindrome. So these letters which are underlined, and what is Q? Q is the overline palindrome. This line is the center of the palindrome P, and this line is the center of the palindrome Q. And how are these mappings defined? If we choose some element, let's say this letter 2, first we map it symmetrically with respect to the center of the palindrome Q. So it is the third letter from the right in Q. It will map to the third letter from the left. Then we map this image with respect to the center of the palindrome PS. it was the, let's say, fourth letter in P. So its image will be the fourth letter in P. 1, 2, 3, 4. This is. And again, with respect to Q, with respect to P, and so on. So this is how these mappings works. And now, what will be the idea? There are some positions that will, let's say, die in the meantime. For example, what happens with these two? This is the second letter in the Q from the right. Okay, its image is the second letter from the left. So this is okay. In P, this is, let's say, the 5th letter from the center. Okay, 1, 2, 3, 4, 5. This is now the image, and now we have to map these letters symmetrical with respect to the center of the palindrome Q, but it is not in Q. So in this case, we say that this position dies. And it can be proved that there are positions in T and V that do not die. And what can happen? It can happen one of the following things. The letter 2 starts his jumpings in V and finishes his jumpings in V. It is the complicated case, and the easiest case is when the letter starts his jumpings in V and finishes in T, which is on this slide, and we will present this case. I hope that it was clear. Okay. So here are some properties of these mappings. The more important one is this, that the sequence sigma 0 n, sigma 2 n, and so on is a strictly decreasing sequence. So if we take every second image of this letter, this will be a strictly increasing sequence. So with this, we can make a partition of the word W. This is the partition. Okay. Now this lemma, the main role of this lemma to bound the length of these intervals that we get. So now we in some way can know how these intervals, how long are these intervals. And finally, this lemma has a role to show that in each of these intervals, let's say there are, let's say, enough many letters too. How we get these letters? These letters will be in some way, let's say, footsteps, the letters from V and from T. So what we have all together, we have some fixed lengths, and in each of these intervals, we have enough many tools. And from this follows that in these intervals, there is not enough many ones, which finishes our proof. Okay, and it's all, and the talk was based on these articles. Thank you for your attention.
Oh, thank you very much. Does anyone have any questions for Kristina or Bojan? I had one question about this result you mentioned by Sari and Holub,
Okay.
that the binary words are characterized up to reversal by their by the set of subpalindromes.
Yes.
So is that false for larger alphabets or unknown for larger alphabets?
It is unknown. We tried to do something with this, and we have only a hypothesis. Our hypothesis is that for the n-ary case, we have n factorial options. So for the ternary case, it will be 6, which sounds okay. It's but for larger arities, it's not a meaningful result, I think. So we didn't prove it, but we think that this holds.
Right. Okay. Anyone else have a question? If not,